Hi everyone, welcome to week 2, Fluid Statics. We're just going to be going through the 5 questions here in the tutorial. Alright, so let's start with the first one. We've got an object that's located in a reservoir filled with fresh water. It's at 2 meters from the top, 2 meters from the water level. Calculate the net uplift if the object is weightless, and calculate the uplift if the object weighs 100 kilos. Alright. So, let's start with our diagrams. Water level, we have an object sitting 2 meters, it's 0.5. Alright, and let's bring this object out. So let's just blow this up a bit and have a look as to what's going on. So this object located in the water, on the top surface here, I have pressure. Hopefully you've all read the course notes. Everything on this x-plane here, x1, has the same pressure. Everything on this plane here, x2, has the same pressure. So the pressure sitting on top of object 1 is the weight of all of the material or the fluid above it. That all pushes down. Everything down here, the pressure on x2, is here for the buoyancy or the uplift. Alright, so that's P1, that's P2. So how do I work out the pressure at this point here? Well, P1, so the pressure along x-plane 1, is equal to rho GH, which is equal to fresh water by 9.81 by 2, which equals 19.62 kPa. So that is the pressure on the top. Now, P2 here going up is slightly different because it's at a lower depth. But remember, every point along x2 is the same pressure. So it's rho GH is equal to 1,000, just the density of water, by gravity, by 2.5, which is the depth, or h, which gives us 24.52 kPa. That is the pressure pushing this object up. Alright, so this is going up, this is going down. So for question A, calculate the net uplift if the object is weightless. So if this weighs nothing, what is the difference between the two? Well, F1, so in terms of force, remember pressure, P is equal to F1A, so therefore F is P times A. So the force 1 equals P1 times A1, which is this area here. And the object was meter by half meter in volume, or in depth, sorry. Okay, so really it's just multiplying by 1. So F1 is 19.62 kilonewtons going down. And F2 is obviously P2A2, which is just 24.52 kilonewtons going up. So how do I calculate the net uplift? Well, the net uplift is simply, so net so no weight, so object is weightless. It's quite simply F2, take F1. Alright, and what that gives us is 24.52 subtract 19.62, all in kilonewtons. This gives us 4.9 kilonewtons. Alright, that is our net uplift if the object is weightless. Just the difference between the two. Now part B, if our object has weight, so the mass of the object is 100 kilos, so therefore the weight is mg, it's 100 by 9.81, which equals, so I'm going to convert it straight away to kilonewtons. Okay, to kilonewtons. Let's move this down a bit. So our net uplift this is with the weight, so with mass, it's equal to F2 subtract F1 subtract W. And all of this equals 3.92 kilonewtons, which makes sense. Alright, what's happening here? So I have an object floating in the water. I account for the water on top of it pushing down. I've got the actual weight of it pushing down, and then I've got the buoyancy pushing back up, and that's why we're subtracting them from each other. Okay, so let's come across and let's do question 2. So question 2 is the pressure at a depth of 2.75 meters in open tank, unknown liquid, what's its density? Alright, so we're given the pressure. Now we're going to work out the density. So again, rearranging these formulas. So we're looking at question 2 now. So I have the tank, I have my fluid, and let's come down, we're going 2.75 meters. And on this plane here, on this X plane, so anywhere along here, my pressure is equal to 42.9 kPa. Alright, so that is along here. How am I going to work that out? Well, I know my pressure at any given point is equal to rho GH. Alright, let's erase that. So therefore, I know my pressure, 42.9, 10 to the 3 gets it to pascals. It's equal to, sorry, we're trying to work out the density. Rho by 9.81 gravity by the height. Rearrange to find the density, therefore density is equal to 1590 kilograms per meter cubed. Easy. Alright, so nice easy way to rearrange the formula. Question 3. Oh, I might have to start erasing these in a minute. Alright, we can come up. It's question 3. Let's go to the question. So we've got a cylindrical tank. It is 1375 high, 750 in diameter. It's sealed. We've got a bit of crude oil in it. We've got a pressure gauge connected 200 ml above the base with a reading on it. What is the pressure in the air above it? Alright, so let's draw a diagram. That always helps. So I have a cylindrical tank, something like this. At the top here, I have a gauge. That's not a very good drawing, Nathan. Let's try that again. Alright, we'll do it like this. We've got a cylindrical tank. At the top, I have a gauge, and that is a unknown pressure. That's what I'm trying to work out. I have some oil sitting in it at some level. I've got some pressure in here, which is obviously causing this gauge to increase. That's what I'm trying to work out. What do I know? I know the height of my container is 1375 millimeters. I know my diameter is 750 millimeters. At some point here, 200 millimeters above, my gauge is reading 9.85 kPa. Alright, and in here, my fluid has an RD, which is 0.86 crude oil, and I have a mass of 370 kilos. Alright, that's all the information that I am given. Sorry. Now let's try to work this out. So, what do I know? Well, I know that rho is equal to m on v. Therefore, mass is equal to rho times the volume. Sorry guys, I just have to get a glass of water. Give me 1 second. Okay, all better. Alright, so mass is equal to rho times the volume. Alright, where volume is just the area times the depth. So therefore, mass, it's not very good. Mass is equal to rho times the area times the depth. What I'm trying to work out is the depth here of the oil. Once I get the depth here, I can work out the pressure that it's causing. Then I can work out the difference. That will make sense as we go through it. So therefore my mass is 370 kilograms, which is equal to my density, which is 860 kilograms per meter cubed, times my area, which is pi by 0.75 squared all over 4. All that times by d. Alright, I'm going to call d being this measurement here as d. So therefore, rearrange, d, or the depth of the crude oil, is 0.9738 millimeters. Just a note here, usually 2 decimal places is significant enough. Because I'm going to use this for further calcs, I'll keep it at this level and then I'll refine at the end. Okay, so I've worked out my depth of my crude oil. Now what I need to know is, I need to know what's happening. Like, I need to know this pressure up here. So what is it? Remember, it's a closed system. So what I know then really is I can base numbers from here. So I go 9.85 times 10 to the 3 to bring it back to pascals is equal to getting a gauge pressure reading here. It has to be equal to this pressure, whatever pressure reading is up here, plus the pressure caused by all of the oil in here. So therefore, P1, I'm going to call this P1. So the pressure that's red at the start, any additional pressure we're adding to the system, plus the pressure caused by the oil. So rho GH, which is 860 times by 9.81 times by the depth 0.9738, subtract this in here. The gauge isn't going to read this. 0.2. It's obviously in pascals. So therefore you rearrange. So P1 is equal to 3.32 kilopascals. And that is how we work out what is up in here. Alright, being a closed system, what I know is simple addition and subtraction. Alright, that is how we've come back to work this out here. Okay, what is next? Question 4. Yep, we can go down here somewhere. Question 4. Right, question 4 is a bit of a beast. Here we are. So a rectangular tank, a couple of horizontal edges on it. This time we're given the volume of the water and the oil. We're going to calculate the pressure at the liquid interface and at the bottom of the tank, which is vented to atmosphere. Okay. So how are we going to do this? Well, let's draw a picture. Pictures are always going to help us get our head around things. I have a tank. And in that tank, I have a level of water. And I have a level of oil. That is a W. Let's write it in. Oil. Alright. My tank measurements. So I have 2.65 here, 1.85 meters here. I don't know the depth of the oil, D1. Don't know the depth of the water, D2. This is what I need to calculate. But what I'm given in the question is V of the water, so my volume of the water is 5.48 meters cubed. I'm also given the volume of the oil, which is 1.99 meters cubed. I'm given that the RD of the oil is 0.866. That's all I'm given. So how do I work this out? Well, remember our volume is simply equal to our area times the height. So therefore, my depth or my height must be my volume divided by my area. Let's try to run with this. So therefore, my D1, the depth of the oil, is equal to my volume of the oil divided by my area, which is these two multiplied by each other. 2.65 times 1.85 meters. What that gives me in turn is 0.4059 meters. It's D1. D2 is obviously the volume of the water. That there is 1.118 meters in depth. So now I've got these. What are we actually after? Well, I need to know at this point here, so on this X plane, So on X1, I need to know the pressure. This is our interface where the oil and the water meet. And at the bottom of the tank, I need to know the pressure down here as well. X2. That's what the question's asking. Alright, where I calculate the pressure at the liquid interface, so where the two liquids meet, and at the bottom of the tank. So where the liquids meet, X1, bottom of the tank, X2. So, what do I know? Well, where the liquids meet, the pressure that I have here is just the weight of the oil. So, where they meet, P1, this is going to be our interface. So the only thing that's acting there is the oil, rho G H, where H is D1, G equals to 0.866 times the water to bring it up to density times 9.81 times by this number here, which is D1, 0.4059. And that pressure there works out to be 3.45 kPa. Alright, that is our first chunk of pressure. Just remember, this here is in gauge pressure. Alright, now at the bottom of the tank, so along X2, so this here is X1, this here is X2, my P2 is easily going to be our P1, so the weight of the oil plus everything to do with the water, which is rho G D2, so the rho of the water, which is 3.45 kPa, which we found before, plus density of water 1.1 by 1.118 times 10 to the negative 3 to get that into kPa as well. What we end up with here is 14.4 kPa in gauge pressure. Alright, so that is our pressure at the bottom of the tank. So we interpret it, we draw a little sketch, crank out our numbers, and then work out our pressures. Alright, now a bit more tricky, let's go to question 5. Last question and we are done. Now this one here is very important. You're going to see a lot of this through the course, and this probably will, more than likely, show up in your exam. So for the tank down here, determine the tension in 6 of the bolts holding the cover plate. This is the cover plate down here. These are the bolt marks that he's talking about. So let's draw our diagram. I have my tank. I need to erase that. I have a plate over here. I see some bolts through it. What else did I have on that diagram? I had a gauge up here reading 20 kPa. I have a water level. So I'm just going back to the diagram. Water level is 2300, height 500, opening, and it's water. Okay. So from here to here, 2300, here to here, 500, This here had a fire of 320. This here is all water. A rho equals 1000. Alright, so trying to find the tension down here. So what I'm trying to find is along this x-plane, the pressure. Okay, again, going to be the same. So my pressure on this x-plane is the pressure, being a closed system, I have 20 kPa that's being punched in straight away. So P1 plus the pressure due to the water, rho GH, which means I have 20 kPa plus 1000 times 9.81 times the height, which is to x1 2300 subtract 500, so 2.3 subtract 0.5 times 10 to the negative 3, get that into kPa. Cool. And this here gives me 37.66 kPa. Now this pressure, remember, is any molecule or any point along this x1 plane has this amount of pressure on it. How do we convert that pressure to a force? Therefore, force is equal to P times A. Therefore, F equals 37.66 kPa times the area. We're talking about the area of this in here now, the area of the gate. I think that's what they call it, a gate, didn't they? Cover plate, sorry. The area of the cover plate, which is pi, because we're given it in a diameter. Pi d squared on 4, 0.32 squared all over 4. This here is going to give us 3028.6 newtons. Times 10 to the 3 gets into newtons. Now what we're asked to do is find the force per bolt. So I have 6 bolts, determine the tension in each of the 6 bolts, so it's per bolt. So simply we go per bolt, so our force per bolt, quite simply 3028.6 divided by 6, and it is roughly 505 newtons per bolt. Alright, so that is our final answer. And if you wanted to, you could go through, you could design the bolts. This is where the question stops, by the way. So you can design the bolts. So how do we design these? Well, our tension fasteners, the axial capacity of it, so area of steel times by the ultimate strength of the steel. Alternatively, you could use a table, and what you'll find is an M12 bolt gives you a reduced capacity in axial tension of the fastener, about 27 kilonewtons. That's per bolt. Alright, so an M12 bolt will absolutely smash this to pieces. If you've got 6 of them, it's very strong. Nonetheless, all you're doing is getting to this point here, and that will finish off your tutorial. Alright, thanks guys, I will see you all in the lecture.